Hello and good afternoon friends, welcome to the CEC-UGC live lecture. Dear friends, as you know that we are carrying a special series on chemical thermodynamics, and so far we have conducted numerous sessions. Dear friends, in this session today we are going to talk on thermodynamics, but as you know that in previous session we talked on the topic matter of thermochemistry, where we studied enthalpy of reactions. We are going to start from the point where we left in our previous session and going to understand more about thermochemistry. And for this, dear friends, we have again with us in our studios Dr. Amit Kumar. Dr. Amit Kumar is Senior Assistant Professor in Department of Chemistry, Dayal Singh College, University of Delhi. So dear friends, let's take advantages from his experiences and let's try to understand more about chemical thermochemistry. That is thermochemistry, which we are going to understand today also. So without wasting any time, I would like to welcome our guest, Dr. Amit Kumar. Dr. Kumar, welcome to the EduSet lecture.
Thank you very much, Kritika. Dear friends, first of all, let me wish very good afternoon to all of you. And as you know, in the previous lecture in the series on the topic matter of thermochemistry, we had dealt with the phase transformation processes. We also tried to understand how the enthalpy change of a phase transformation process occurs, and in fact it is a first order phase transition, that is fusion process, or similar other phase transitions such as sublimation or vaporization, for which enthalpy change we try to define, following which for a chemical reaction we try to define the enthalpy of a reaction. We would like to, and we also like to see is that whether a reaction is exothermic or endothermic, it certainly has extent of reaction that makes an important criteria to determine the enthalpy of a reaction. That is how an extent of reaction is a topic matter of chemical kinetics that is used to monitor the chemical reaction, but how we make use of that aspect in defining the enthalpy of a reaction, that becomes an important consideration in at the undergraduate level. Let us have a look at it again. You see, in the previous lecture, as we had observed that enthalpy of a reaction basically was formulated as the stoichiometric times the molar enthalpy of products, that is their sum, from which the stoichiometric times the molar enthalpy of the reactants were subtracted. So basically you can say that enthalpy of products less the enthalpy of reactants basically is the enthalpy of reaction. However, we defined it in a different manner. We said that enthalpy of a reaction is the heat change accompanying the unit extent of reaction, or the enthalpy change accompanying a chemical reaction for unit extent of reaction. So now extent of reaction, we defined it in a very elusive manner in the previous lecture. So now what is its meaning in the practical sense? Let us have a look at this reaction where 2 moles of C2H2 is being consumed, that is it undergoes combustion reaction, that it combines with 5 moles of oxygen and produces 4 moles of carbon dioxide along with 2 moles of water in the liquid state also gets produced. Basically this is a thermochemical equation. Thermochemical equation has an important criteria to be written, and how it is different from chemical reactions is that it is important to specify the physical state of each and every reactant and product which do participate in a chemical reaction. So thermochemical reaction and a chemical reaction, the difference between the two is that you need to specify the physical state of each and every reactant and product participating in the chemical reaction. Moreover, it needs to be balanced, and it can be balanced in a number of ways. That we will also see how we can balance a chemical reaction in different number of ways. For example, I am having 2 moles, the stoichiometric coefficient of C2H2 here is 2, whereas for oxygen the stoichiometric coefficient is 5. 4 represent the stoichiometric coefficient for carbon dioxide, and again 2 is being the stoichiometric coefficient of H2O. But if you see, if we multiply the whole equation by a numeric value, that is 2. So, the stoichiometric coefficients of each and every chemical reaction in that situation will get doubled, but the chemical reaction will again be a balanced chemical reaction. So, what I am trying to say is that the chemical reaction can be balanced just by having different multiples of stoichiometric coefficient. What it means is that is if we want to understand the meaning of this different balancing of chemical reactions in a thermochemical reaction, we need to understand the unit extent of reaction. What we actually mean by saying this? Unit extent of reaction means, suppose if we write a thermochemical equation by writing all the reactant species at the left hand side which do participate in the chemical reaction and the products on the right hand side, and also if we write the stoichiometric coefficient such that the each and every element which is present in the left hand side and the right hand side, their number is being the same. In such a situation, we will say the chemical equation is balanced. So, it means, suppose for example, if we have just this thermochemical equation, it means that 2 moles of C2H2 has been consumed as well as 5 moles of oxygen, and this has led to production of 4 moles of carbon dioxide and 2 moles of water vapor, water in the liquid state. We may start with different number of moles, or different number of moles could also be consumed. We can just here write again another thermochemical equation where we can write 4 instead of 2 as the stoichiometric coefficient for C2H2 and 10 for the oxygen. Then it means the stoichiometric coefficient would get doubled. So, the unit extent of reaction means the reaction has progressed to 1 mole. It means that the number of moles of the reactant species corresponding to the stoichiometric coefficients have been consumed, and the number of moles of the product chemical species have been produced that correspond to their respective stoichiometric coefficient, again in the balanced chemical equation, thermochemical equation. So, whenever we want to describe the enthalpy of a reaction, it is important that first of all our job is to write the thermochemical equation. If we balance it in a different manner, then again it will be a different thermochemical equation, and then in that situation the enthalpy change accompanying, which was accompanying the previous reaction, would get doubled if we multiply the earlier equation by 2. This is all I wanted to convey about the extent of reaction. So, unit extent of reaction means the number of moles of reactants which has been written as the stoichiometric coefficient in a balanced thermochemical equation, they have been consumed, and the number of moles of the participating product chemical species have been produced. Having said this, if we further switch over our attention to standard values, let us have a look at the standard values of thermodynamic properties. The standard value of a thermodynamic property basically is the magnitude of this thermodynamic property at a standard pressure value, and standard pressure value earlier it used to be 1 atmosphere pressure, which was defined at the sea level. Because of that it has now been accepted by International Union of Pure and Applied Chemistry that 1 bar instead of 1 atmosphere will represent the standard value of pressure. Moreover, standard values of thermodynamic properties used to be defined under standard pressure, that is 1 atmosphere, and at definite temperature 298 Kelvin, but nowadays it has been accepted by International Union of Pure and Applied Chemistry that any if we talk about any standard thermodynamic value or a standard value of any thermodynamic property, it means we are talking about the numeric value of this thermodynamic property at 1 bar pressure, and temperature has no concern about its definition. It means we can define the standard value of any thermodynamic property at a desired temperature. So, it need not necessarily be 298 Kelvin, which earlier used to be the situation. Now, having said this, let us now switch over our attention to the fact that molar enthalpy is basically the molar enthalpies of products and reactants are an important criteria for determination of enthalpy of a reaction. That is, enthalpy of a reaction basically is the sum of molar enthalpies of products less the molar enthalpies of the reactants. But we also emphasized that it is determination of absolute molar enthalpy values of various chemical species is not possible. So, now the question comes, if for those reactions for which determination of enthalpy change cannot be carried out experimentally, then in that situation it means we cannot determine the enthalpy change of such reactions. But there is a rescue also. The rescue lies in the definition of another important property, that is called enthalpy of formation. Just have a look at it, what way we define the enthalpy of formation. We define the standard enthalpy of formation as the enthalpy change accompanying the formation of 1 mole of a pure compound from its constituent elements. For example, if we talk about carbon dioxide as a compound, then the enthalpy change for this formation of 1 mole of carbon dioxide from carbon and oxygen represent the enthalpy of formation, because in that reaction carbon and oxygen serve as the elements which we make use of, which they do react and then do form carbon dioxide. So, definition, it is important to note that the definition of standard enthalpy of formation requires that if we write a balanced chemical equation, then at the right hand side there should be the stoichiometric coefficient of the product, that is the compound, the desirable compound should be 1. That is, we want to determine the enthalpy change just in the case of formation of only 1 mole of the compound. Having said this, it is further important to note that enthalpy of formation of pure elements in their standard state is considered as 0. Now, the question arises, it means that formation of elements would not take any enthalpy change. It means the heat would not be involved in the formation of elements. It is a complete misconception. It is complete misconception in the sense that we are not trying to say that enthalpy of formation of pure elements in their standard state is 0, but we say that enthalpy of formation of pure elements in their standard state, that is under 1 bar pressure, is considered as 0. And why it is considered as 0, we will see it very shortly. So, before we proceed any further, we take examples of standard states also. For example, the standard enthalpy of formation of an element in its most stable form is considered as 0. Now, we need to understand that which is the most stable state of an element under standard conditions, that is 1 bar. For example, oxygen could be a molecular dioxygen, could be ozone, could be oxygen atom. We need to understand which of these three chemical species, which can be considered as their elemental form is the most stable under standard conditions at 1 bar pressure and at desired temperature. So, at 1 bar pressure, molecular dioxygen is the most stable form of the elemental oxygen. So, therefore, standard enthalpy of formation of oxygen would be considered as 0, but it is not that standard enthalpy of formation of ozone would not be considered as 0. There is some value to the standard enthalpy of formation of ozone, which is not there for standard enthalpy of formation of oxygen, because oxygen is the most stable state of aggregation of elemental oxygen under standard conditions, that is 1 bar and at 298 Kelvin. That is the desired temperature. We can change the temperature also, because oxygen would exist, molecular dioxygen would exist over a range of temperature under standard conditions, that is 1 bar pressure. Now, coming over to the comparison of carbon, which is the most stable state of aggregation of carbon in its elemental form. because we all know diamond and graphite both exist at standard conditions, that is 1 bar pressure and 298 Kelvin, or in other words the room temperature, the 25 degree Celsius. Graphite we can also have, the diamonds we can also have. Now, what is the factor which will determine which is the most stable state of aggregation? It is not that both these have same Gibbs free energy considerations, but the fact of matter is one form is more stable, that is graphite, because it has lower Gibbs free energy. Molar Gibbs free energy of graphite is lower than that of molar Gibbs free energy of diamond. So, now the question arises, will that be true that if diamonds are just placed in a room they will get converted to graphite? Is it true? It is not true, because had it been so, all the jewelers would have been ruined. So, the fact of matter is that it is, although this reaction is possible, but now question here, this transformation question is that this transformation never occurs. At least we have not seen in our whole lifetime this transformation of diamonds converting to graphite. This is because of the kinetic considerations that we learn in the chemical kinetics chapter, because diamonds are stable because of kinetic considerations and graphite is stable because of thermodynamic considerations, and in thermodynamics we talk about thermodynamic stability, and most stable state of aggregation of matter is the one which is considered thermodynamically. So, graphite is the most stable state of aggregation thermodynamically, and therefore, its enthalpy of formation would be considered as 0. Now, let us have a look at writing formation reactions and how we can make use of formation reactions in order to determine the enthalpy changes accompanying a particular chemical reaction. The formation reaction, for example, for carbon monoxide is the reaction between the elements in the compounds, that is the carbon and oxygen, which do react to form carbon monoxide in the gaseous state. The elements must be in their standard states. Now, it means the carbon should be in the form of graphite and oxygen should be in the form of molecular dioxygen. So, it does mean that carbon here in the solid phase should be as graphite and oxygen should be as molecular dioxygen in the gaseous species, and when it forms carbon monoxide in the product side, and 1 mole of carbon monoxide is formed according to this thermochemical equation. So, now this we have as a balanced thermochemical equation, and this equation predicts that 1 mole of carbon monoxide is getting formed. So, this reaction can be considered as formation reaction. The equation must be balanced. Now, the question arises, is this balanced? This next equation, carbon solid graphite plus half oxygen O2 to carbon monoxide, or this equation is balanced? Here there are 2 atoms of oxygen at the left hand side, whereas only right hand side has only 1 atom of oxygen. So, the idea is that since this equation is not balanced, now we can introduce the balancing in the equation by multiplying a half integral value, that is 1 by 2 as the stoichiometric coefficient to the preceding the oxygen in the gaseous state. So, this is the way we can write the thermochemical equation, and this thermochemical equation would then represent the formation reaction. For the formation of 1 mole of carbon monoxide, please note that to the product side there is only 1 mole of the product, the only product whose formation we are talking about is present. So, the characteristic of a formation reaction is that there will be only one chemical species in the product side, and it may be possible that in order to achieve a unity as the stoichiometric coefficient in the balanced chemical equation, it may be possible that the various participating chemical species, that is the reactants, may have integral values or may have any fractional values of stoichiometric coefficients also. So, having said this, so we can see that enthalpy of formation of silver in the solid phase is the substance that is most stable state of aggregation under standard condition for silver. So, its molar enthalpy of formation is considered as 0. For aluminium again is 0. So, all elements, that is, these are the metals, these are all elements whose enthalpy in their most stable state of aggregation under standard conditions is considered as 0. Now, coming over to the discussion of the fact that how we can make use of enthalpy of formation and what is basically the purpose of defining. You see, earlier formation is also a reaction, formation of a compound is also a reaction. Now, the question arises, why we are considering a particular reaction as a formation reaction and we are introducing one more concept in the thermochemistry subject matter. So, let us have a look at it, what it means actually and what way it can help us. As you have already seen that for any reaction, the enthalpy of the reaction is basically the sum of molar enthalpies of products less the sum of molar enthalpies of reactants. So, therefore, formation reaction is also just a reaction just like any other reaction, but just we have, since there is only one chemical species in the product side. So, we have just, and although it is moreover its stoichiometric coefficient is just 1. So, therefore, we are saying we have just defined that enthalpy of formation equal to molar enthalpy of compounds which are present in the product side less the sum of molar enthalpies of all the reactants which go to react to form the constituent compound. Now, we can rearrange this equation also. We can take this molar enthalpy of the compound which is under consideration as the formed compound to the left hand side, or then it becomes molar and standard molar enthalpy of the compound which is equal to its enthalpy of formation, added to which is the all the terms that are actually the standard molar enthalpies of all the reactants, their sum. And we all know standard molar enthalpies of all the reactants being the elements in their most stable state of aggregation. So, they would be considered as 0. So, therefore, enthalpy of formation of a compound under standard conditions would actually be the standard molar enthalpy of that compound, provided the molar enthalpy of the elements in their most stable state of aggregation which is being considered as 0 makes no interference in any further calculation. We will try to see how they do not make any interference, and this idea helps in our calculation of enthalpy of reactions. So, before we proceed any further, let us apply this equation, that is molar enthalpy of a compound equal to enthalpy of its formation plus the sum of molar enthalpies of the reactants which go to form the compound. Let us apply this formula to the reaction in which molecular dihydrogen that combines with oxygen and forms water in the liquid state. Let us have a look at it. We can write the enthalpy of formation for this reaction, that is delta HF standard, that is equal to molar enthalpy of water in liquid state minus standard molar enthalpy of hydrogen gas, added to which is the half of standard molar enthalpy of oxygen gas. Basically, the fact of matter is that we can further rearrange this equation, and we can take this standard molar enthalpy of water in liquid state to the left hand side, and it becomes standard molar enthalpy of water in the liquid state. That is, by rearranging this equation, we get standard molar enthalpy of water in liquid state equal to standard molar enthalpy of hydrogen gas plus half standard molar enthalpy of oxygen gas. In addition, we also need to add the standard molar enthalpy of formation of water in the liquid state. Basically, therefore, as a generalization we can say the standard molar enthalpy of any compound is any chemical compound basically is equal to the standard molar enthalpy of formation of this compound plus the sum of all the molar enthalpies of the constituent elements in their stable state of aggregation, which when we considered as 0. So, in that sense the molar enthalpy of formation of the compound becomes its molar enthalpy itself. But the question arises, why we require this assignment of 0 value to the molar enthalpy of a particular reactant, that is the elements. Why we assign a 0 value to the molar and standard molar enthalpy of elements in their stable state of aggregation? This is a question that we wish to address. Before we address this question, let us have a look at it, how we make use of calculation of standard enthalpy of formation in order to calculate the standard enthalpies of other reactions. Basically, I have already told you that standard enthalpy of a particular reaction basically is the sum of molar enthalpies of products less the molar enthalpies of reactants. But it is not possible to determine standard molar enthalpies, or in fact the molar enthalpies of absolute values of molar enthalpies of any substance. So, therefore, it means we cannot determine the enthalpy of a reaction. But if we try to determine the enthalpy of formation of a compound experimentally, and in that situation the molar enthalpy of the compound will be the molar enthalpy of formation of that compound. We have already seen just in the previous slide. You see, we have said if molar enthalpy of the elements, or in other words the reactants, the elements in their stable state of aggregation, if they are assigned a 0 value, so this summation term becomes 0 and enthalpy of formation becomes equal to the molar enthalpy of the compound. So, it means if we try to determine molar enthalpy of formation of any compound experimentally, then it will be just treated as its molar enthalpy, and then in that situation we can tabulate the value of this molar enthalpy of formation of the compound determined experimentally as its molar enthalpy in the calculation of some other reaction enthalpies in which this particular chemical species would be participating. So, it means the enthalpy of reaction would actually then be the sum of their stoichiometric times the enthalpy of formation of the various product species less the sum of stoichiometric times the enthalpy of formation of the reactants. So, basically now you can see, if we are not being able to determine enthalpy of reaction by virtue of our inability to determine the absolute values of molar enthalpies, then we can still calculate the enthalpy of a reaction by tabulating the value of molar enthalpy of formation by using this formula, standard molar enthalpy of a reaction, which is equal to sum of stoichiometric times the molar enthalpy of formation of products minus the sum of stoichiometric coefficient times the molar enthalpy of formation of reactants. So, this way you can see that enthalpy of formation is a very important tool for determining enthalpy of reaction for certain unknown reactions. We can have a further look at what basically is an enthalpy of formation and how it is helpful in determining the enthalpy of a reaction. Suppose we have a particular chemical reaction in which we have some reactants and their enthalpies are at this level, and this is how at the y axis you can see it varies the enthalpy, and the maximum value of enthalpy suppose is 0, because if why 0, it is again a question. At 0 level we have elements in their standard state. I am not saying the molar enthalpy of elements in their standard states would be 0. Again it should be mentioned that this is considered as 0, they would not be 0. So, let us suppose they are 0, then when reactants go to decompose to form elements again, they would require that same enthalpy which were obtained as during their formation. The same enthalpy would be the enthalpy of decomposition with a negative sign. So, now enthalpy of formation of a compound from its element in standard state is that we have suppose elements in their standard state at 0 level of enthalpy, if we say that they are, suppose they are present at 0 level, when a compound forms, the enthalpy change occurs, that is delta H, there occurs a change in enthalpy. So, suppose this is the change in enthalpy from elements to the product side, and suppose this is the change in enthalpy from elements to the reactant side. So, when reactant, we are just, therefore, we are just altering the path. So, reactants would be having certain molar enthalpy shown by this level, products would be having certain molar enthalpies shown by this level. If we cannot determine their exact enthalpies of reactants and products, their absolute values, then at least we can determine experimentally, if it is possible, that we can determine their enthalpies of formation. So, negative of enthalpies of formation of reactants and positive of enthalpies of formation of reactants, the difference you can clearly see will represent the enthalpy of the reaction. And since you can see the enthalpy of reactants is higher, the sum of enthalpies of products is lower in the enthalpy diagram. So, therefore, it means this is a diagram, representative diagram for an exothermic reaction, in which delta RH has a negative value. The heat gets produced during such reactions. Similarly, for an endothermic reaction, same way we can, if we, our objective is to calculate enthalpy of reaction, standard enthalpy of reaction, that is delta RH. And how we can calculate it? We just take the difference of two terms, that is enthalpy of formation of products and enthalpy of formation of reactants. So, enthalpy of formation of products has, you can see, this much value change, and this is the enthalpy of formation of reactants which have this much value change. So, therefore, if we take the difference of two value changes, then it becomes the difference basically in transforming from reactant side to the product side, and this actually represent the delta RH standard. Therefore, delta RH standard is equal to delta HF standard minus delta HF standard reactants. So, basically, we can easily, from these diagrams, the equation is rationalized, as we said earlier, that enthalpy of any reaction basically is the sum of stoichiometric coefficient times the standard enthalpy of formation of products minus sum of stoichiometric coefficient times the standard enthalpy of formation of reactants. Having said this, now let us have a look at how we can calculate these enthalpies. Let us suppose we want to calculate enthalpy change in this reaction, that is C2H2 when combines with oxygen, that is combustion of C2H2. So, all we need is enthalpy of formation of C2H2, and now question arises, do we need enthalpy of formation of oxygen? My answer to this is no, because we are considering molecular dioxygen under standard condition is the most stable state of aggregate of oxygen. So, therefore, enthalpy of formation of oxygen would be considered 0, and enthalpy of we need further data on enthalpy of formation of carbon dioxide, and also we need enthalpy of formation of water in the liquid state. So, state is very important. This was highlighted upon the previous lecture, and also in this lecture that thermochemical equation requires that we represent the physical state of all the substances which do participate in the chemical reaction. Having said this, just have a look. If we want to determine the enthalpy change, standard enthalpy change of this reaction, then all we need to do is we need to write the sum of stoichiometric times the stoichiometric coefficient times the enthalpy of formation of products. Now, how many chemical species we have in the product side? We have two chemical species, one is carbon dioxide and the other is water in the liquid state. So, all we need to do is we need to multiply 4 as the stoichiometric coefficient with the enthalpy of formation of carbon dioxide, then we have to add to this is the multiple factor stoichiometric coefficient 2 times the enthalpy of formation of water, and therefore, this represent the value at the product side. Now, coming over to the reactant side, again we have two reactants, the 2 is the stoichiometric coefficient for the C2H2, then we need to multiply 2 with delta HF C2H2, that is enthalpy of formation of C2H2, plus 5 is the stoichiometric coefficient for molecular dioxygen here as the reactant. So, we will multiply 5 with enthalpy of formation of oxygen. But since as you can see when we tabulate the data, enthalpy of formation for carbon dioxide being minus 393.5 kilojoule per mole and enthalpy of formation of water in the liquid state, mind you, is minus 285.8 kilojoule per mole, and from which we can subtract 2 times enthalpy of formation of C2H2, which is plus. Now, you can see the enthalpies of formation of both the reactants were exothermic in nature, whereas the enthalpy of formation of our reactant of both these products are enthalpy of formation of both these products are exothermic in nature, whereas the formation reaction for our reactant C2H2 is an endothermic process, because we have just seen the tabulated data, that is plus 227.4 kilojoule per mole. Now, coming over to the enthalpy of formation of oxygen, as I said, molecular oxygen is the most stable state of aggregation under standard condition of elemental oxygen. So, therefore, it would be considered as 0. So, we are just tabulating this 0 kilojoule per mole, and whenever we work out this algebraic calculation, then it sums to enthalpy of reaction as minus 2600.4 kilojoule per mole. So, you can easily see we have determined the enthalpy of this reaction, enthalpy change accompanying this reaction without the use of molar enthalpies of products and reactants, rather their enthalpies of formation. But now question arises, why the molar enthalpy of formation of a particular element in its most stable state under standard condition is being considered as 0. This is question yet which is facing us. So, let us try to figure out the answer to this question. In order to figure out the answer to this question, let us consider a reaction, that is Fe2O3 in the solid state when combines with hydrogen, and it forms iron, that is Fe in the solid state, and it also leads to formation of water in the liquid state. So, we are now considering this reaction, and you can see this reaction has one compound Fe2O3 which is used as reactant, and we have hydrogen which is acting as elemental hydrogen, because in the gaseous state hydrogen is the most stable, molecular dihydrogen is the most stable state of aggregation of hydrogen under standard conditions, that is 1 bar pressure. So, this leads in this reaction, it leads to formation of iron in the solid phase, and it also leads to formation of water as a compound in the liquid state. So, we can say that in both the products and reactant sides we have two chemical species, and one product is a compound, the other product is an elemental form of iron. Whereas, if we talk about reactants, then Fe2O3 is a compound and molecular dihydrogen basically is a element in its most stable state of aggregation under standard conditions. So, if we talk about the standard enthalpy of this reaction, basically it means the enthalpy of this reaction equal to sum of enthalpies of products minus sum of enthalpies of reactants. It is written other way round, but it should be actually sum of molar enthalpies of products minus sum of molar enthalpies of reactants. It is written other way round. So, there is a little correction in this representation. Therefore, for the reaction given above, for this reaction we can write the enthalpy of reaction as molar 2, which is the stoichiometric coefficient of iron in the balanced chemical equation 2 into molar enthalpy, standard molar enthalpy of iron plus 3, which is the stoichiometric coefficient for water, multiplied we will multiply it with molar enthalpy of water in liquid state, and so this sum becomes the molar enthalpies of products, from which we need to subtract the molar enthalpies of reactants. So, we place a negative sign, and inside bracket we take as molar enthalpies of the two participating species as their sum of molar enthalpies of reactants. So, molar enthalpy, standard molar enthalpy of Fe2O3 3 in solid phase, because its stoichiometric coefficient is just 1. So, we have just 1 here, and plus we have stoichiometric coefficient of molecular dihydrogen as 3 in the balanced chemical equation. So, we write here 3 into standard molar enthalpy of hydrogen. So, now as we have already seen that standard enthalpy of formation equal to standard enthalpy of compound minus sum of standard molar enthalpies of reactants, that is the elements in stable state of aggregation. Let us see how we rearrange and how we make use of equation 4 in equation number 3. Let us have a look at it. When we rearrange this equation number 4, what we get is standard molar enthalpies of a compound, that is equal to enthalpy of formation of the compound plus sum of standard molar enthalpies of the reactants. Let us apply again to this formation reaction water. We can determine the standard molar enthalpy of water as the standard molar enthalpy of hydrogen plus half standard molar enthalpy of oxygen plus standard molar enthalpy of formation of water in liquid state. Similarly, we can determine standard molar enthalpy of Fe2O3, that is as equal to just by rearranging, by writing standard molar enthalpy of formation and then rearranging it, that is equal to 2 into standard molar enthalpy of iron plus 3 by 2 into standard molar enthalpy of oxygen plus enthalpy of formation of Fe2O3. So, in these equation number 7 and 9, you can easily see the last term means standard molar enthalpy of formation of water and Fe2O3, which we can determine experimentally. Now, and what it is correlated to? It is correlated to standard molar enthalpy of water and standard molar enthalpy of Fe2O3. So, we can make use of equation 7 and equation 8 in equation number 3. What is equation number 3? Equation number 3 is enthalpy of this reaction. So, in this enthalpy of this reaction, we have molar enthalpy values of various product species and various reactant species. So, in place of writing molar enthalpies of water, standard molar enthalpy and standard molar enthalpy of Fe2O3, we just replace these two terms by their respective equations as written in equation number 7 and equation number 9. What we ultimately get is our equation 3 by virtue of this substitution becomes this equation. Have a look at it, what we have done. Delta RH, equation number 3 and this big equation, they are analogous forms. All we have done is that delta RH here, delta RH standard equal to 2 times standard molar enthalpy of iron plus 3 times, instead of standard molar enthalpy of water in liquid state, what we have written standard molar enthalpy of hydrogen gas plus half standard molar enthalpy of oxygen, and we have also written plus standard molar enthalpy of formation of water in liquid state. Similarly, instead of standard molar enthalpy of Fe2O3, we have substituted this expression, which involves standard molar enthalpy of iron, standard molar enthalpy of oxygen gas and standard molar enthalpy of formation of Fe2O3. Now, if we cancel like terms in this equation, what we will get as the enthalpy of reaction basically equal to the enthalpy of formation of water in liquid state and enthalpy from which we need to subtract enthalpy of formation of standard enthalpy of formation of Fe2O3. Otherwise, you see 2 into standard molar enthalpy of iron, which is present here and is also present here, but both these standard molar enthalpies of iron has opposite signs, so they will cancel here. Similarly, standard molar enthalpies of hydrogen having the same stoichiometric coefficient here and here, they will also cancel, and standard molar enthalpy of oxygen here, as that is multiplied with 3 here. So, 3 by 2 standard molar enthalpy of oxygen, which has plus sign, plus minus sign times 3 by 2 standard molar enthalpy of oxygen. So, these two terms will also do cancel. So, what we will ultimately have, that standard molar enthalpy of this overall reaction equal to standard molar enthalpy of formation of water minus the standard molar enthalpy of formation of Fe2O3 in solid state. So, by virtue of working out this derivation, what we have tried to understand is that in this enthalpy of reaction, standard enthalpy of reaction, although in equation 3 was utilizing the data on molar enthalpy of the products, that is the which were having compound as well as elements in their stable state of aggregation, but they did not figure in whenever we try to replace molar enthalpies of compounds in terms of molar enthalpy of formation of these compounds, added to which is the sum of molar enthalpies of respective elements. So, all these element term cancel, and what we are left with in a particular reaction as the enthalpy change of a reaction becomes equal to the enthalpy of formation of products minus the enthalpy of formation of reactants. So, elemental enthalpies does not figure in the enthalpy of reaction expression. This is all we wanted to understand from this working out of derivation. So, we can conclude the enthalpy change in any chemical reaction does not depend on the molar enthalpy values of elements that compose the compound. This is the reason that we may assign any arbitrary convenient value to the molar enthalpy of elements in their reference state or their stable state of aggregation at any given temperature and pressure. Since the value of molar enthalpy of elements does not matter in the calculation of enthalpy of reaction in which they participate, the enthalpy of every element in its most stable state of aggregation under 1 bar pressure and at any specified temperature is assigned a 0 value. So, basically what we are trying to say is that since the molar enthalpy values of elements does not figure out in the expression of enthalpy change of a reaction, so we can assign them any arbitrary value, and in order to remove the numerical clutter we assign a simplest value, that is 0, that is 0. So, standard values, standard molar enthalpies of elements in their most stable state of aggregation is considered as 0, that is not 0, but actually because they does not figure in the calculation of enthalpies of various other reactions. So, we consider them, the molar enthalpies of elements in their reference state, we consider them as 0. So, this is how we have been able to address why standard molar enthalpies of elements are considered as 0. So, but the question arises, basically there are certain reactions for which enthalpies of formation is easy to determine experimentally using thermochemical experiments, but there are certain reactions for which determination of enthalpy of formation from experimental considerations becomes very difficult or almost impossible. The major difficulty in the calculation of in the determination of standard molar enthalpies of formation lies in the fact that we can understand by virtue of this exemplar reaction, that is, if suppose we have graphite and we combine it with hydrogen, it will form methane, we write it as this reaction. So, as such the way this reaction is written, it gives us an information that 1 mole of graphite is being utilized and 2 moles of hydrogen has been utilized to form 1 mole of methane. So, it looks very simple as the reaction is written, but the inherent problem with experimental part of this reaction is that combination of graphite with hydrogen does not occur readily. It is not easy to carry reaction, it does not occur so quickly. So, if the reaction is managed in a calorimeter, if suppose we by virtue of adjustment of reaction conditions, if we manage to allow this reaction to occur in calorimeter, the product would not be pure methane. Why? Because when graphite, the carbon in the form of graphite reacts with hydrogen, it is not that only methane it will form an exceedingly complex mixture of hydrocarbons. There will be other hydrocarbons which will also form. So, that will lead to a basically major practical difficulty. Then what we will need to do is, we will need to analyze the product mixtures, what products have been formed, and even if we try to do that, and even if we are being able to succeed in that analysis of what products have been formed, then it would be almost impossible experimentally to interpret the data, that is how much is the enthalpy change has accompanied with the formation of a particular compound, that is methane. So, basically whenever we utilize, I want to pinpoint here an important fact, that whenever we want to utilize enthalpy of formation data for the calculation of enthalpies of reaction, and which we can do by experimental determination of enthalpy of formation of compounds, it is important that formation reaction is achieved such that no side reactions occur in the system, and only in the reaction system the elements should combine and they should produce only a single product species, that is a pure compound at the, it is a desired fact. If it is not true, then if it leads to a mixture of compounds, then it becomes difficult to analyze the mixture and it would introduce the hindrance to our determination of enthalpy of formation. So, the fact of matter is that for many reactions it is almost impossible that we are being able to determine enthalpy of formation experimentally, but for that is formation of carbon dioxide, for formation of water from hydrogen and oxygen, that those two reactions along with several others we can achieve the determination, experimental determination of enthalpy of formation with precision. So, now we were using enthalpy of formation as at our rescue in order to determine the enthalpy of reaction. So, now the enthalpy of formation in itself, determination of enthalpy of formation in itself is a difficulty. So, what to do now? So, the rescue now lies in calculation and determination, experimental determination of certain other enthalpies of reactions. Those reactions are combustion reactions. So, let us talk about them, how we can utilize the experimental determination of combustion reactions to determine the molar enthalpies, or in other words the enthalpies of formation of certain compounds. Let us have a look at it. Let us consider the combustion reaction now instead of formation reaction of methane, where we required 1 mole of graphite to combine with 2 mole of hydrogen to form 1 mole of methane, which we cannot because of experimental considerations, which we cannot determine enthalpies of this formation reaction experimentally. So, let us carry out combustion reaction. Combustion reactions occurs in definite proportion. Combustion reactions are the one in which we take certain amount of combustible product and which would be combined with definite amount of oxygen that is just required to completely react with the given amount, that is defined amount of the particular compound whose combustion we wish to study. And when the reaction between a compound and the oxygen, that is the combustion reaction, occurs, it lead to a definite mixture of, that is particularly in the case of hydrocarbons, that will lead to formation of carbon dioxide and water. So, this would be a reaction which would occur in definite proportion with the formation of only carbon dioxide and water, that is combustion reaction of hydrocarbons. So, when this combustion reaction of hydrocarbon occurs, this lead to formation of carbon dioxide and water. And now, let us write enthalpy of reaction for this particular reaction. Enthalpy for this reaction, because carbon dioxide and water is just been in the product side. So, molar enthalpy of carbon dioxide plus the stoichiometric times 2, that is the 2 is the stoichiometric coefficient for water in the product side. So, molar enthalpy of water in liquid state, from which we need to subtract the standard molar enthalpy of methane in the gaseous state. So, basically this represents the enthalpy of reaction, and since the reaction we have specified as combustion, which require only 1 mole of the compound to be taken as its reaction with oxygen as the combustion reaction. So, we represent the enthalpy of reaction as delta H standard comp. Comp in the subscript represent this is the combustion reaction. So, now we can rearrange this equation, and we can take delta H standard comp to the right hand side, and we can bring delta H and we can bring HM standard, the standard molar enthalpy of methane, to the left hand side, and this therefore becomes equal to molar enthalpy of carbon dioxide plus 2 times molar enthalpy of water in liquid state minus molar enthalpy of combustion of methane. Enthalpy of combustion of methane we can determine experimentally, and enthalpy of formation we can determine of water and carbon dioxide we can determine experimentally, and their enthalpies of formation basically is the standard molar enthalpies of water and carbon dioxide, and just tabulating the experimental data we can accurately calculate the standard molar enthalpy of methane in the gaseous state. Just by tabulating minus 393, you can see 2 times minus 285 for molar and standard molar enthalpy of water in liquid state minus the standard molar enthalpy of combustion of methane, that is minus 890.26 kilojoule. All these values lies in kilojoule per mole. So, therefore, this amounts to standard molar enthalpy as minus 74.81 kilojoule per mole. There can be other calculations also. For example, if we want to calculate standard enthalpy of formation of carbon disulfide in liquid state, then all we can do in that is, if we have the given data, that is the enthalpy of combustion of enthalpy of formation of carbon dioxide, enthalpy of formation of sulfur dioxide, and enthalpy of combustion of carbon disulfide. So, basically we are utilizing the enthalpies of combustion of the compounds in order to determine their enthalpies of formation. Just see, we have these 3 chemical reactions as enthalpy of formation of carbon dioxide and sulfur dioxide, and enthalpy of combustion of carbon disulfide. All we can do is we can rearrange them. For example, we can write enthalpy of formation for CS2 as C graphite plus 2S rhombic, because now here we have written S rhombic. Why rhombic? There are 2 forms of sulfur, that is, otherwise there are 4 forms under at room temperature. You can see under standard conditions we have 2 forms, one is rhombic and monoclinic. So, here rhombic we have written because it is most stable state of aggregation of sulfur under standard condition at room temperature. So, we have written 2S rhombic, and C we have written graphite, that gives 1 mole of CS2. So, basically this is the formation reaction for which we desire the enthalpy of formation of CS2. So, we can manipulate these 3 reactions, that is, we can write equation 1, we can write 2 times equation 2, and add to this, we can add to this is the reverse of equation 3, and therefore we can manipulate the enthalpies of these respective reactions in the same manner, that is enthalpy of reaction 1 plus 2 times enthalpy of reaction 2, and we can add to this is the opposite sign, that is, now you can see enthalpy of reaction of this third reaction is minus 1072 kilojoule per mole, but here we have written as plus 1072 kilojoule. Why? Because this reaction we have reversed, and when we take the sum of these 3 reactions, then it becomes the enthalpies of the enthalpy change accompanying this overall reaction, which is nothing but carbon graphite plus 2 sulfur rhombic to CS2 liquid, which is the desired reaction, and therefore manipulating the enthalpies of these 3 respective reactions, we can get the enthalpy of this overall reaction, which will therefore serve as our enthalpy of formation of carbon disulfide. So, basically what I wanted to say is that we can make use of enthalpy of formation in order to calculate the enthalpy of reaction of certain unknown reactions. Instead, if enthalpy of formation data is not is not present with us, is difficult to determine experimentally, the enthalpy of combustion can also be made use of, and using which we can determine enthalpy of formation, and therefore the standard molar enthalpies of various substances, which ultimately lead to the which allows us to calculate the standard molar enthalpies of reactions, the unknown reactions. So, these three data sets helps us to calculate enthalpies of reaction in this manner. Thank you very much, and following this we will continue in our next lecture.
With this note, thank you sir, thank you so very much for giving your time as well as precious input to this very lecture on thermodynamics. As Dr. Kumar himself said that we would be conducting more sessions and we would be discussing more on thermodynamics. Dear friends, if you want to give your feedback regarding this particular lecture, then you can mail us at info.cc@nic.in, and if you want to access this particular lecture, then very soon we are going to upload this lecture on YouTube, with the help of which you can access this lecture, and likewise you can give your feedbacks as well as you can ask any question through email, that is info.cc@nic.in. We would be meeting again. Till then, take care. Goodbye. Thank you sir. Thank you so very much.